In the second part of the sorting unit, we'll look at ways to be a little opportunistic, if you like. If the input has already some partial sortedness, a good sorting algorithm should try to take advantage of that. And we'll call that adaptive sorting as well. And let's start from first principles on this in a way. Remember, we're back to the comparison-based model just because it gives us versatile algorithms. If it's comparison-based, you can apply it to anything that you sort. There's nothing more general. If you can sort at all, you can sort it with comparisons. Other things might take advantage of, say, the objects being integers. But the most versatile algorithms are comparison-based. So we like that model, which means we can't possibly beat this lower bound in the worst case. Even more, if you analyze these comparison trees more closely, you can also show that it's not just that the longest route to leaf path has this length. It's actually the average length as well. You can't have most elements higher up. That gives you the same contradiction. So this lower bound I've shown you based on the comparison trees also gives you the same, virtually the same bound, rounded down instead of rounded up for the average case. So it seems if you pick some random input, random in the sense of randomly shuffled, then this is the cost you will have to pay. Quicksort and Mergesort are close to that in the average case, but even in the best case, they still use n log n. That basically follows from their divide and conquer nature. It's at least in time. So the code that I've shown you will not get faster even if the input is very easy. So you could think about if we can do anything about that. What can we do if the input is already almost sorted? And what does that actually mean? There's different ways how you can formalize this. But instead of starting from definitions, I want to show you some example applications why it naturally arises in some cases that you want to sort something, but it's not completely random. One thing can be it is basically merging different data sources where each of those has a natural tendency to be sorted. For example, log files from different servers and you want to collate those. There will be some sortedness, or they're almost sorted. But then if you take them together, you have to somehow merge them in a way. Another application could be if you have a time series, some sensor data that you measure. Usually, say, a temperature sensor doesn't jump too much in short time increments. So there's some way of a dependency on time. It might not be that it's completely sorted, right? It might go up and down. But there's some local sortedness in such data. Kind of the similar point as the first one, but framed in a different way or in a different application. Things like distributed computing frameworks that well, without going into any detail of these, they often work by bringing together data from different sources because they're distributed across different computers. And so you have to bring them back into one collated thing, which often means sorting. Question?
Yeah, to answer the question you said about like how you can do better, like my 5-second bet, like instead of like sorting individual elements, if you sorted list, like you could go over the array and then like break the array into chunks that are already contiguous chunks that are already sorted. And then you can apply Peeksort or Mergesort over those contiguous chunks instead of over an individual element array.
Yeah, okay, so the suggestion was to take sorted chunks and use those as the basis of sorting. That's what we'll do. You will see there's some there's some subtleties in doing that. There's other ways how you could define pre-sortedness. It's basically a vague term. You could come up with whatever definition of that. You could also say is sorted with few elements that you only have to move. But I think from these applications, what you suggest is most natural. They're local chunks that are already in order. So let's try to exploit that bit. So how could we do this? A very simple way would be if the input is completely sorted already, we don't have to do anything. So we could check for that case. I mean, it's fairly cheap. This, compared to n log n, n-1 comparisons is not so much. But of course, it's very limited, right? You only get the completely sorted case fine. Maybe you can add a second special case for the reversely sorted one. And do you want to keep going, like add more of these? Question?
Yeah, well, yeah, so like could start from this iteration, then build a new service. Instead, like you trade time for space. So you could like, let's say you have like a dictionary or something. So you start with the first element, and then you start appending a new list with all the solid elements. So when you reach a new element out of order, you add a new entry to the dictionary and then append like that. So you have like a dictionary of sub-sorted lists or a list of sub-sorted lists. So you could do this pass over directly. But instead of like handling that one special case, you handle all cases where they are sub-sorted, they are chunked already sorted.
Okay, so the suggestion is to kind of, while you check if it's completely sorted, if something's not sorted, you kind of put it in another bucket in some way or another. I think most methods do something like this. The trick usually is you want to do all of this in a way, like I always phrase it like this. You come up with some super clever scenario to etch out some cases. But then by the time you figure out what to do, Quicksort says, oh, I'm done, by the way. You need to do something really, really low overhead. I'm not saying this is not the way to go, but you need to be really careful about not causing a lot of extra effort before you before you get going with the sorting. Okay, so this was just like that's not a sensible suggestion, right? This is as a first very simple thing to do. You can check if you're already done and then stop, but that's very specific. Now, the algorithms we've seen, I didn't stress that point too much, but you may have heard of divide and conquer. I touched on this at the beginning a bit. The algorithms we have seen, quicksort, mergesort, they all are recursive. So they could do this kind of step in each recursive subcall. And then suddenly the whole idea becomes a little more interesting because you're not only capturing this, the whole thing is already sorted, but some subrange that you recurse on is sorted. So you could stop at that point in the recursion tree. So that's a little better. The thing is, if you repeatedly check for sortedness and do this at every level, you're at least doubling the cost or something like that. You add overhead that is on the order of what you pay for sorting. So that's probably going to be like what I said before, right? You keep going like this. You're very happy that you could skip a few subtrees, but you're halfway through and Quicksort says, I'm done. So we want to do this with less overhead. And I don't think this is possible in a black box way. But if we look at the two algorithms we've seen in more detail, you may see that for Mergesort, we can do this much cheaper. Mergesort has the nice feature. It first sorts left and right half, and then we come back and merge the two. Now, if we're lucky, everything in the left run is smaller than everything in the right run. And we can find out whether that's the case with a single comparison. Just take the biggest in the left run and the smallest in the right run and compare them. If they are already in order, we don't need to do the merging step. It's already done. This doesn't save the recursive calls, unfortunately. But we'll apply the same strategy in the recursive calls. So they do still get cheaper if there is pre-sortedness in there. So it's a very simple idea, I think. And like you naturally are led there from a really bogus idea to something that has promise, at least. This is just copied the Mergesort code from a couple of slides back. With all the animations, probably a couple of hundred slides back. But there's only one line added. That's the comparison that I mentioned. So how good is this? In this subsection, I don't want to go too deep on the analysis. So let's have a look at some indicative examples, say. What we'll use as our cost measure is not the number of comparisons, but something slightly simpler to analyze, the merge cost. So merge cost is just the size of the output of a merge. By and large, that's the same as the number of comparisons in the worst case. But if you're merging, sometimes you're lucky and you run out of one run. And then the remainder of the second run, you could just copy over without further comparisons. So you would kind of always have to say, oh, at most. And so this is inconvenient. Merge cost is always the same. And if you like that justification better, merge cost is the effort to produce the output in the array. You have to write the elements there. You're copying them, even if they were already from the same run. You still have to copy them over to the buffer. So that's just to simplify the discussion, if you like. Is essentially the memory transfers that might be more expensive in practice anyways. Okay, so here's some input. It might be too small to read, but you see that this is sorted up to this point. And then the next two, these are sorted, and this is sorted, and this is sorted. I kept things very nice, so it's a power of 2 in total. It's a power of 2 in each. So of course, Mergesort doesn't know this, right? It starts and doing its thing. And here I drew the recursion tree for Mergesort, where so Mergesort would start here and say, let's split in the middle, call two recursive calls for the left and right half. What I also drew is this vertical bar, which is just a visual representation for merge cost, because that's the size of the output of this recursive call. At the topmost level, we at the end produce in sorted order the entire list. The left recursive call of this top call produces the left half, and so on and so forth. Okay, it's another way of showing what Mergesort did. But it's so far exactly what we discussed back then. And you can just sum up the sizes of all these gray blobs. And again, you see nicely this is the same at each level. They just fill up the entire space on each level. So it's n, the size, times the height of this tree. And that's log n because we keep cutting in half. Okay? If you sum this up for this concrete example, you get this, this number. And if we do our fancy new version with the sortedness check, it cuts that down to a third by basically stopping at this point, right? This merge we would still have to do. But at this point, we're entirely within this sorted part. I will call these sorted parts runs, as we used that term for merge sort when we discussed how merging works. We said there's 2 runs, and now we merge that into one big sorted list. So we could as well call this one run. Okay, it's on the slides. And this recursive call will not have to do anything. It will start here, call itself recursively on the left and the right half, blub, 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 all the way down. And then for these 2 individual elements, it comes back and says, oh, I don't have to merge you guys. You're already in order. Happy. So it passes control back up. Same thing happens here. Control passes back up for the first 4 elements. Oh, you're also in order. So you keep going up. If you look at the number of comparisons you pay, it's a bit awkward to account for them because they happen at different levels in the recursion. But you're really just using the minimal number of comparisons to find out that this is sorted anyways. If you project down these nodes, you compare every 2 consecutive elements over the course of the recursive calls. Okay? And so in this case, this happens for all those. So all of these, I grayed out the bar because there's no merging happening. So in terms of merge cost, all these recursive calls are for free. In terms of comparisons, they're not exactly for free, but they wouldn't cost n log n, they would cost n minus 1. So merge cost, again, ignores this, so it's a little easier to keep numbers. Good so far? We like sortedness check? Yeah.
Does this change the asymptotic, or does it just make the constant better?
Pardon? So it's...
Does this change the asymptotics, or does it just make the constant factor better?
So that's a tough question. The question was, does this change the asymptotics or just the constant factor? The answer is it depends on the input. Simple answer to your question. If the input is already sorted, it does change the asymptotics, because then it works out to do just n minus 1 comparisons and no merge cost at all. So depending on the choice of the cost measure, it's either for free or linear time, as opposed to n log n. What happens in between, if it's not entirely sorted but some bits are sorted, it all depends on how much is sorted. The detailed analysis for this concrete algorithm is a tiny little tricky, and I'll show you why. Okay, I do have some bits of the analysis. Let's do that first and pretend we're in the picture from before. If we have this nice scenario like before, all runs are the same length, say L. In terms of merge cost, not doing all these merges saved us exactly what Mergesort would have used to sort those, which would have been L log L. So we save the cost of creating this run if it already is sorted. So we can say we take the overall number, the overall merge cost of merge sort, if there was no sortedness check, and we subtract what we save, which in the good case of the slide before is exactly the length of the runs. Well, Li times log of that, because that's the cost Mergesort would have needed to spend to create that run. All right. Okay, let's give this quantity a name. If you have an input with run lengths L1 to LR, then h of these lengths is just this this difference. Now the tricky bit with this is it works for the example on the previous slide that Mergesort has exactly this cost. It doesn't work in general. So here I have the same kind of setup. So it's maybe a bit hard to see. So here are the run boundaries. If you have good eyes, you may spot that this is not exactly split in quarters. Instead, this is one short, or yeah. So this is 15, and another 15, and then two 17, I guess. So the total length is the same, but the run boundaries are slightly moved around. And now you don't get exactly such a nice picture. There's a few other recursive calls that need to merge. And in a way, for a stupid reason, right? This call here would really have to just include one more element into its run, but it doesn't know that, so it doesn't exploit that fact. And you see, if you add up the numbers, then this doesn't look quite as good as we had it before. Intuitively, you could say the run boundary can cast this ray upwards, and whenever that ray crosses the merge node, then you have to keep that and do the merge. All right. You can try to analyze this a little better. That might be a nice student project. For now, I would just leave it with that, saying this would be great, but the simple merge sort we have so far doesn't always get there. Question?
Yeah. Is there any way to determine, just like outline, is there a cheap way to determine what the ideal one boundary would be from the data? Or like, is that not possible? It's able to die cheaply. Like, after you can see, okay, this even this level of sortedness, this kind of boundaries would be good for.
Yeah, since 3 years ago or 4 years ago by now, definitely yes. Okay, I'll show you how soon. There's one step in between. So if you see this, it sounds just really stupid to insist on cutting things exactly in half at each recursive call if that doesn't align with the run boundaries we find in the input. That's definitely the cause of this overhead. So let's try to get away from that. So there's another way to do merge sort that we may not have talked about so much, but you'll. So this is a slight hint for the tutorial question. This week has a lot of like fun puzzles. Sorting with your right hand tied on the back in a way. And maybe this code will help. Don't want to spoil it by much more. You can do merge sort bottom up instead of starting at the root with a recursive call and then cutting things in half. You can start with individual elements and say, okay, my first task is instead of individual elements, I'll make pairs that are sorted. So I go first two, sort them all the way through. And then you have everything paired up so that two consecutive elements are always sorted. Now you have runs of length 2. So you can take the first two runs, each of two elements, merge those into one run of length 4. If you spell that out, that's what this code does. So maybe let's do a tiny example on just say 8 elements. That's not 8. That's called bottom-up merge sort, if you've seen this before. Maybe I should have said, well, the slide says so, but and what's currently on the slide, ignore this for now. That will come on the next bit. This is straight bottom-up merge sort with no twists. So you start out with treating each element as a single run of its own. The next round would take 2 of them and merge them. So you end up with 4 runs of 2 elements each. Then you take, again, 2 of these runs and make them to runs of 4. I'm just drawing these boxes to show that these are in sorted order, right? You should fill in proper numbers and so on, but you've seen my drawing skills, so let's leave it with that. And then the last point is turn that into one big sorted list. No recursion. No recursion needed. You can do this. You can organize that process, for example, in this way. So you start with, you keep a queue of things to do in this phase. You initially put individual elements in the queue. So what is in the queue formally is always start and end index of runs. This puts individual elements inside. Then you run through the queue. You always take 2 elements out. You merge them, and you put them into a new queue for the next phase. So again, if we look at what we did here, so this is the queue initially. We fill it with all the runs. We take those 2 out, produce the merged result, and add that to a new queue. And we take the next 2 and add that behind this, and so on and so forth. So you get exactly this kind of pattern of merges. Okay, and you keep doing this. Do we ever stop? Yeah, while yeah, okay, so this will eventually terminate. Good. You don't create a new queue. The standard mode is you keep creating a new queue, which will have half as many runs. And at some point, you will have a queue with just the sorted list. And in that case, you don't stop, right? So maybe this code needs fixing and to terminate. I'll double check, but the key part is yep. Yeah, it happily packs the full array into the new queue and keeps looping. Apologies for that, but it's easy to fix. You just need another if, which might blow up the size on the slide. I tried to squeeze this already a bit. The key point I want to get to here, though, is you don't need recursion and you don't need to split in the middle. You can let this organically happen bottom up. And so the insight for natural bottom-up merge sort is, instead of starting with individual elements, let's try to find the runs that are in the input and use those. So that's what this does. It finds the longest sorted segment starting at this point. Just keep going as long as the things are nicely increasing. And then you put that in the queue instead of the individual elements. That sounds pretty smart, right? No, I mean, you kind of maybe guess what happens. So if we look at the example that did not work so well with the top-down merge sort and sortedness check, that was this example. If we look at the same example with the new idea, it works brilliantly because you detect this run, you detect this run, and this, and you nicely merge them up. So instead of paying this 216, you pay 128, which is very close to what we had, was very close to this H quantity, which was our kind of idealized goal. If we could always perfectly save as much as merge sort would have had to spend to create that run, that's intuitively best possible.
That like the lower bound of what can be like on the optimal.
This one? The H? Yeah, you can prove that this is a lower bound with some little bit of a noise term. But by and large, that's a lower bound, definitely for merge cost. Right, so that sounds good. Now, unfortunately, there's another problem with this new method. What if your input is like this? One really long run, and then a lot of noise at the end. Think about the log files. Maybe you keep a log file, you sort this every day, and then you append new random things. Why would you sort a log file? Well, maybe some database. You have updates at the end, and you want to, at some point, sort this for the next join operation. So this doesn't look too made up to me, to say it like carefully. Now our bottom-up merge sort has a problem. It doesn't really take into account how long these runs are, and so it will merge this really long run many times, which blows up the cost. If you compare that again with our first method, the top-down with sortedness check, that seems to work much better here. So we have two methods now, neither of which is really satisfactory in all cases. And I've just shown a few examples, right? You can, maybe there's a third one where both are not so great. So it seems somehow this is not really the solution. We would really like to have the good behavior in one single method. And so sometimes it can help to go back to first principles and think about what we want. We like the idea of picking up existing runs.
For that I think what we want ideally is to leave the first the one that's sorted untouched, then apply a certain algorithm to the last of the list, and then combine it at the last step. Ideally, you don't touch it until you sorted the last one.
Yeah, it's a good comment. I'll repeat it for the recording. So what we intuitively want here is not mess around with this long run many times. Keep that separate, sort the rest, and then merge. Very true. The trick, of course, is where's the cutoff? What if you have two fairly long runs? It seems like this is an endless game of special cases. So what I thought at this point is, let's go a step back and see what we really want. We liked the idea of picking up existing runs because that's, after all, what we're trying to do, exploit the sortedness that is there. So we have to somehow find that and not just randomly stumble over it as the top-down method. But then these runs that we do find can have vastly different lengths, and so it would be stupid to ignore that. Turned on its head, we want a smart way to order the merges that we have to do. And so this seemed to work well in the top-down method because this splitting in half made sure that the trees never get too tall. And bottom-up doesn't have this property. So somehow we would like to get these two things. So maybe instead of working from existing methods and tweaking them a little, let's try to find a new method. Just to make this, all right, so this first step, finding runs, bottom-up merge sort already did that, right? That's not our worry, that's not hard. The tricky bit is to find a good order of the merges, in particular if they have weird patterns of length, small, long, weirdly intermixed. Now, any order of merges at the end of the day will look like this. In other ways, in other terms, it is a binary tree. Every merge replaces two runs with a longer run and can itself be used in more merges. So it's nodes that have a left and a right child, the first and the second run. And it also has this property that we don't want to merge, say, the first run and the very last one together in one step. The reason for that is that we want to keep stability. Remember, one of the selling points for Mergesort was that it's stable. If you have equal elements, they stay in the relative order. You can think about this if you have merges across, if you have elements in the middle and you merge these two, no matter how you deal with them, you will lose stability because you don't know what's in the middle. You could move things to the front or to the back and both could break stability. However, if you always merge adjacent runs, you don't get this problem. And these two things together mean all that we're looking at is find a good binary tree on top of these runs that defines a good merge order. And what's a good merge order? It's one where if you sum up all the sizes of these gray bars, that's the cost, and we want to minimize that. The total area of these boxes. All right? And now suddenly this is a well-defined problem. Question?
For natural and that bottom of Mergesort, what will be the space complexity? Like I can see that this bottom of has a large amount of queues we are using. So does it contain more space?
Okay, the question was if bottom-up Mergesort needs more space. I would say not much. You need a little bit of space for the queue, so you need n pointers or something like that. You also had the buffer area of roughly size n, so you could argue it needs more space than top-down. Also, top-down is not entirely for free. You need the recursion stack, but that's logarithmic as opposed to linear. So I give you that one. Bottom-up has extra cost for the queue. Now, I wonder if you can somehow be smart and avoid having the queue in the first place. It's much nicer to describe that way. If you don't do the natural one, you don't need the queue. Because the run boundaries are regular, you can just compute them on the fly. With existing runs, I don't see how to do it right away, but you know, people can be smart. But it's a fair point. Bottom-up has this slight blemish of needing the queue. Okay, so in this case, the second looks like a well-defined optimization problem. The only trouble is we want to spend very, very little time on solving it. Otherwise, again, quicksort, hey, I'm done. You're still finding out your merge order. Good luck with that. All right. We can reformulate the problem a little bit. Instead of saying this is all these black boxes, we can say that's the total length of the path from the root to all the entries in the array. That happens to be the same thing. And why is that the case? So we would take each of these numbers and sum up how many steps we have to go down from the root. It's the same because if you look up from any one element, it occurred in 2 boxes before, so it contributed a factor of 2 to the cost before, and now it contributes 1, 2, because that's its depth in the tree. So it's not anything really intelligent. It's just a different way of writing the cost. Instead of saying we sum up at the node level, we sum up at the element level. And so you can write this by saying, okay, I don't really care that these are different elements in the array. I can just say this leaf has weight 6 because there's 6 elements. Its depth is counted 6 times. So you can write it as a fancy sum if you want. You sum over all leaves. And what do you sum? The weight of the leaf times its depth. All right. Now this is the point where you want to study algorithms, and sometimes esoteric topics from the 70s turn out to be useful. It turns out people have studied this problem. It's exactly the same as asking for the best binary search tree. So the model there is you have leaves. So the null pointers, the unsuccessful searches in the tree have weights. There's some probability that you need to find how would that make sense? Suppose you store a set of numbers and you want to find out for a new number, between what 2 numbers does it lie of the numbers that are stored? Why? Well, because I want you to do that. I don't have a great application at this point. Maybe I should think of one that's more intuitive. So you have a set of numbers, and for any new number you want to find with the fewest number of comparisons, between which of the 2 numbers does it lie? And you have some assumption that certain questions are more likely than others. Certain of the gaps have a higher probability of being asked than others. Finding the best binary search tree over those numbers to solve this question is exactly the same as our question of minimizing this cost. This is maybe not obvious, but if you spell it, if you write it down, you get just exactly the same term that you try to minimize. So what I'm getting at here is just, this is a problem that people have studied and they have solutions for it. So you can use those and try to use them to find fast a good merging order. And that's what I did with my postdoc supervisor 4 years ago. And so we found two cool new methods that are much faster than and have nice properties compared to this top-down and bottom-up attempts that we've seen. Okay. Let me show you the first one, because that one is, I think, a little more intuitive. It's called Peeksort because it peaks in the middle of the array. We liked top-down merge sort in principle. The only problem was it was blind to the run boundaries. So instead of doing that, you jump to the middle of your array and find the run that contains this position. You can do that by just scanning to the right and continue as long as these are increasing, continue to the left as long as this is decreasing. So you find some sorted portion. And this may be of any size, you don't know, right? But it has some boundaries. And now the idea is just take the closer boundary and make that the cut of the topmost recursive call. So you cut at this point because that's closer to the middle. And well, okay, you cut, and that becomes the left and right of merge sort's recursive calls. And the rest is unchanged. You don't even need this sortedness check anymore, because you'll make sure that you don't recurse on a sorted list by the same peaking step anyways. If the middle is contained in a run that is the entire thing, you're done. So let's see this on this example, how it continues. So you peak in the middle of this recursive call again. You would cut at the closer boundary. Same on the right. If you continue doing this, you get that kind of tree. Is it clear how the process will work? So what I'm drawing with these red boxes is the runs, right? The numbers are omitted, but it's really an array, and you would have to find the sorted segments. But the code for that is the same as for bottom-up merge sort. Okay, so it sounds like a fairly simple way to do. If you want to implement this, you can try to be a little smart and avoid finding a run twice. It could sometimes happen in weird cases that you would scan the same run twice. And so we can avoid that by remembering what's the leftmost and rightmost run. So how could this happen if you find this long run and you do this recursive call? This is the run that we've discovered at the topmost call. In this recursive call, we would jump to the middle and we would rediscover the very same run. That's kind of wasted effort. We could have remembered that there was a run. And so that's exactly what I'm proposing here. You just remember if you have seen a run at the end points. And it turns out that this is enough. So you remember what's the leftmost run, the rightmost run of any portion, and that's all you'll ever need. And they could both be empty. Okay, I think it's getting late and you look a little confused. So I think this is, that's the full code for this, but I don't want to go into detail. I just want to convince you that it fits on a slide. It's not too hard to spell it out in details so that you can just program it down. But the intuition is the bit I want you to take from it. Yeah, I think no much more comments on the code. So the only nasty bit is if you have these 2 points, you have a run you already know about in the left end and on the right end, both of which could be not there because you haven't seen anything there. That gives you a bunch of different cases. And so these 2 if-else statements here, they handle all those cases. That's the only complication. What I haven't shown you is how well does this work. From what I've shown you so far, it's just jump in the middle and cut. Sounds intuitively reasonable. I haven't motivated much more than that, whether that's good. So let's look at this more tricky input from before, that bottom-up merge sort really blew and top-down merge sort did a little better. If you do this with Peeksort, so how would it go, right? This is the middle, so you would find this run. So you would cut off this really big run, as you suggested before. And then on the right-hand side, it's a little more even split because the runs are of similar lengths. So this naturally or organically or automatically finds such kind of intuitively sensible cut points. And it's very close to this H bound. You can prove that the merge class is essentially this minimal H plus at most 2n from a little bit of overhead that you sometimes have. And that was basically just reading again what people invented in the 70s. The same trick of peaking the middle works for binary search trees because they're the same problem.